Section 2.5, solutions by substitutions. What I want to do is to try to cover, if I can, about 3 to 4 problems in this section because of my time limitation. And then when we come back the next day to review, if I miss a problem, I definitely go over it on the next class time. Okay. There are several types of substitutions in differential equations. I think the simplest one would be what's called a homogeneous differential equation. Homogeneous, the word homo here meaning one, genesis or of the same origin. And so if there's a problem where I think the easiest way to understand it is, you know how you have dy and dx, and you have terms associated with dy, terms associated with dx. If the powers that's associated with dx and dy, those coefficients, and we say coefficients here in differential equations, we're not just talking about numbers, we're talking about functions really. But if those coefficients have the same power, they're said to be, of the same, then we say that that differential equation is homogeneous. Let me scroll down and just show you what I'm talking about. Take number 1 down there. This is x minus y, x to the first power, y to the first power. This is x times dy, x to the first power. So same term, same power type. So here we call that homogeneous. Matter of fact, keep looking at all the problems. This is x to the first power, y minus 2x. Here, power of 1. They could be power of 2. It could be x times y, and it could be x squared or y squared. As long as we have that consistency, we say it's homogeneous. That's all they're talking about. Well, that one is as well. But look at number 11. That's a good one. Here, this is x times y squared. So here, the power in terms of the big O for algorithmic purposes would be the power of 3. Right? Then you look at y to the third, x to the third. So in that sense, it's homogeneous. We can use the substitution that the homogeneous differential equations stipulate. So let me go over that with you. Now, the definition for homogeneous equations is given here: a function f that has the property that f of some parameter tx comma ty, if that's equal to, if the t factors can all factor out, some t to the nth power times the original function f of xy. We say that the function f is said to be homogeneous in nth degree. So if we could do that, then you got it. Well, as a matter of fact, just based on what I said earlier about the powers, that'll always be the case. You won't get a common factor of t to the n if you got some terms are raised to the second power and then some terms raised to the first power. You won't get that commonality. If it is homogeneous, and the funny thing about this section is that they kind of tell you, okay, it's a homogeneous problem, and you solve it, so you kind of know. Sometimes you may not know, but you can just check that very simple schematic flow. If all the coefficients of dy and dx have common powers, then you have the idea of a homogeneous function. A differential equation of the form m dx plus n dy equals 0 is said to be homogeneous if both coefficients, m and n, are homogeneous of the same degree. If that is the case, how are you going to solve a homogeneous differential equation? Well, make sure that it is homogeneous. We call this the property of homogeneity. The property is important. I don't know if the students who took linear algebra last semester, we got into the inner product spaces. We had one of those clauses in there that said homogeneity. It's the same idea. What does that mean for us in differential equations? That means that these functions would form a linear algebra, basically. You got to have homogeneity for the linear algebra, homogeneity, positivity. and then some type of symmetry, and then the existence of a zero vector. Anyway, if it's homogeneous, you want to use a substitution. We call it an appropriate substitution because it could be either this y equal to ux, or you could use x equal to vy. Which one is really your choice. Doesn't matter. Doesn't matter. But I put my note here to say that if you want to make it easy on yourself, make it easy on yourself. When you look at, m and n, m is some function of x and y, and n is some function of x and y. Look at those guys. Look at dx and dy. If dx, just count the dx's, how many do I have? Count the dy's. If dx occurs least compared to dy, if dx occurs least compared to dy, then you use x equal to vy. It's going to make the substitution and the simplification easier. If the dy's occurs less than the number of dx's, then you use y equal to ux. Okay. Now again, it does not matter. You'll get the same result, but if you do the opposite of what I'm saying, you just get there in a longer time. Okay, just take you a little while longer. So that note there, I think, is pretty important. Now the question is, what if you have the same number of dx's as you have the number of dy's? You can have 2 dx's, 2 dy's. Doesn't matter, right? Doesn't matter which one you use for the substitution. Only use one substitution, by the way. Because if you use both the substitutions, then you get the same thing that you had before, right? A problem that you can't solve. That's why we use substitution, so we can actually solve it, right? Yeah. All right. So let's see if we can work this out. Okay, I put a problem here, the first one. See, like I said, each differential equation in problems 1 through 14 is homogeneous. Well, why are you telling me that? So it kind of defeats the whole idea, so you don't have to even determine if it's homogeneous or not. On this problem, let me go on the side and show you how that property of homogeneity would be important. Here, in the old book, he had problems where you had to actually show this property. I guess now he thought that it's not important. But if we take x minus y, if you take the x here, so if you replace the x with t times x, replace the y with t times y, so we have x minus y here times a t, and then over here we have this t times x. So this is tx minus ty, and this is just tx. And for this problem, it's very easy because it's just x minus y and x, so you don't really see the use of it. And I should have written this as 1, and then 2, and then you replace x with t times x, replace y with t times y, and then try to factor out the t. So here we have and so if we get the same form from before, just with the factor term of t coming out, then we say that it is homogeneous. Of degree n equal 1, because this is t to the first power. Well, he doesn't make this a big issue in this textbook, and so I won't either. And on the test, I typically would ask, for that particular property, and I won't. So I just erase that. We just work the problem. So let's see. If it's homogeneous, yes it is. Now look at this. This is x dx minus y dx plus x dy equal to 0. I have two dx's, I have one dy. So I'm going to say let y equal to, all right? Let y equal to ux. And we just differentiate. So this is dy is equal to, take the derivative, this is u dx plus x du. Right? So wherever I have y, I'm going to write ux. Wherever I have dy, I'm going to write the expression u dx plus x dy. X du. I get my y's and u's mixed up in my head, but I write the right thing. I may say something stupid, so just pray for me. So this is x dx, that's the first term, minus here the y, it's going to be ux dx plus x parentheses u dx plus x du equal to 0. We'll just simplify. X dx minus ux dx plus xu dx plus x squared du equal to 0. Now ux dx and xu dx, they're the same, so we cancel out. Then we keep working. We have x dx plus x squared du is equal to 0. Now, after you do that substitution, typically what happens is the problem will boil down to a separation of variables problem. Separate the variables and just solve. So here, to do that, if you divide everything through by x squared, I get 1 over x dx plus du is equal to 0. We integrate. If you want to get the terms on opposite sides, like in the idea of separation of variables, that's fine. So here I'm going to subtract 1 over x dx on both sides. It just gives me negative 1 over x dx is equal to du. Somebody has to be negative. You can put the negative on the du side, it doesn't matter. So this is negative natural log absolute value of x is equal to u, and that was a plus c behind that natural log of x too. Yeah, not everything. Plus c is equal to u. We integrate it, right? Separate the variables. So this u came from up here. And so u is equal to y over x. So we have negative natural log of the absolute value of x plus c is equal to y over x. Just multiply through by an x. So we get y is equal to c times x minus x times the natural log of x, or the absolute value of x. Okay. Any questions there? Let's take number 5. It seems to be more to it. Number 3 kind of reminds us of the previous problem, so let's look at something a little bit different. Let's take number 5. So here, this will be y squared dx plus yx dx. So I have 2 dx's. I have 1 dy. So we'll let y equal to ux. Differentiate this substitution. So this is dy is equal to u dx plus x du. So wherever I have y, I'm going to replace that with ux. So this is u squared x squared plus this becomes ux times x, or u times x squared dx minus x squared times parentheses u dx plus x du. This equal to 0. Well, let's simplify this. This is u squared x squared dx plus ux squared dx minus ux squared dx. Almost sounds like you're cursing somebody, ux squared. But anyway, dx. This is minus, you got to have a little fun with this stuff, folks, I tell you. So minus x cubed du equal to 0. You know what happened if you call somebody a ux squared? Nothing. But anyway. So let's see. I think the terms here will cancel out. The ux squared dx minus ux squared dx will cancel, so we can get rid of those. Sometimes you'll have cancellation with this substitution. Sometimes you won't. So don't really, look for it because it just might not be. It just so happens with these 2 problems that I'm working, we're getting some terms that cancel out. So u squared x squared dx minus x cubed du is equal to 0. We separate the variables now. So to do that, we divide through by x squared, u squared, and then divide through by x cubed. So dividing through by the x cubed and the u squared, we get x squared divided by x cubed is 1 over x dx minus 1 over u squared du equal to 0. This is 1 over x dx is equal to 1 over u squared du. Integrate both sides. So we get the natural log of the absolute value of x is equal to, this is u to the negative 2, so that becomes, when you integrate that, u to the negative 2 plus 1, so that's u to the negative 1 divided by a negative 1, so this is negative 1 over u, and I forgot to put that c over there associated with the x. We tend to associate the constants with the x terms. So we have y was equal to ux. That implies that u is equal to y over x. So we make the substitution. This is negative 1 over y over x, or negative x over y. Multiply everything here by the y. So we get y times the natural log of the absolute value of x plus this c times y is equal to negative x. You see, you had that selection of where to put the c. If you put the c over by the u, then the answer will look different, but it'll still be equivalent. So what if you were working it over here, and you said that your answer was the natural log of the absolute value of x is equal to negative 1 over u plus c. I mean, that's fine too. This is the natural log of the absolute value of x. Is equal to negative x over y plus c, and you can write that as negative x plus cy all over y. Multiply both sides by the y. We get y times the natural log of the absolute value of x is equal to cy minus x, or you can say that this is simply x plus y times the natural log of x is equal to cy. I think that's the answer that he has in the back of the book. They look different, right? You know. So what if you had this part on the left? Now, for Weber sign, it's supposed to recognize both of those. So if you put in what I have on the left side or the right side, you should be fine. And then obviously on the test, you know, I'm not nitpicky either. So if you have your answer like what I have on the left or the right, is fine. I was taught that when you're writing your solutions, the constant term is always associated on the same sign with the independent variable, which is typically x. So I would have put my c over here with that natural log of x, and my answer would have looked like that. Which then I would look in the back of the book and I'll say, holy moly, you know, my answer is not the same. Well, it is. It's equivalent. It's just written a little bit different, right? Okay. Any questions? They got some more problems there, and what I do is on the next day I'll work one of those that I didn't work here. Let me go on to Bernoulli Equations, and I just do one problem with Bernoulli because it's kind of like a long process. Bernoulli Equations of this form. It begs for the idea of a linear differential equation. dy over dx plus p of xy, that's good. But then equal to f of x, that's good. But y times y to the n, that's a uh-oh. Right? Well, that factor over there kind of throws us off. And so we ask the question, what do we do with it? Well, you can just do like how my friends used to do in school. They would just erase it. But we don't have that property anymore, the eraser property, right? Just get rid of it. Okay, it's linear. Just solve it like the old way. No, I'm sorry. I wrote out the steps. The author did not put the steps in, so I thought best to put them in for you. We're going to write, make sure that the differential equation is in this form of equation number 4, that it looks just like that. If it does, then the first thing you're going to do is you're going to divide everything through by that y to the n. So that's my second step. Divide each term by y to the n. Now, with these steps and with the notations, it looks kind of like a whole lot of stuff, and really is not. So let me just go ahead and just do the problem and show you how these steps work out. So it won't scare you too bad then. You know, you see all these X's and Y's and N's and alphas and betas and gammas and let me just change my major to history, of which I love history, by the way. But anyway, let me get back to this problem. Okay. And so as I work the problem, I will explain these steps as we go along. This is number 15. So I'm going to first write it in the form. So here's the form here. Divide everything through by that x. I'm just going to write y prime. This is plus 1 over x times y is equal to 1 over x times this 1 over y squared. Right? So now this guy is in the form. So the next step says you got to get rid of this y term on that right side over there. Whatever that is multiplied times f of x. F of x here would be 1 over x. This is 1 over y squared. So it says divide through by that, but since it's 1 over y squared, we're multiplying everything by y squared. So when you do that, you have y squared times y prime plus 1 over x. So y times y squared is y to the third. That's equal to 1 over x. So 2, that's supposed to be a 3. Okay. So when you get here, the substitution comes in. Whatever this term is times the p of x. So whatever you have there, this is y to the third. I'm going to put my substitution on that. Because if you do that, its derivative will give you the y squared y prime. Always, automatically. So here we say, let u equal to y to the third. Differentiate through here, so this gives us u prime is equal to 3 y squared times y prime. Now up in the problem is y squared y prime. It's not a 3, so I can write this as 1/3 times u prime is equal to y squared times y prime. So I'm going to make my substitution here in this problem. So here I have y squared y prime. That's going to be 1/3 u prime. So it's 1/3 u prime plus 1 over x. This y to the third was claimed to be u. So this is u, not u, but u, right? Okay. This is equal to, anyway. This is equal to 1 over x. I'm trying to make this guy look like a linear equation. It's not linear yet. Multiply everything by 3 and it will be. It'll be linear in this u. So multiply everything by 3. I get u prime plus 3 over x times u is equal to 3 over x. So this equation here is said to be linear in u. So if that be the case, its integrating factor, mu is equal to e to the integral of p of x here, which is 3 over x dx. Integrate that, we get 3 times the natural log of x, or e to the natural log of x cubed. And that just gives us x cubed. So now we multiply everything through by the integrating factor. So this is x cubed times this u prime plus 3 over x times the integrating factor x cubed times u, that's equal to 3 over x times x cubed. The left side, remember, is always automatically the derivative of the product of the integrating factor and the dependent variable. So this is the derivative of the product of the integrating factor, which is x to the third, and u is the independent guy. This is equal to 3x squared. Integrate both sides. So this gives us x to the third times u. We integrate that side over there. This is 3 times, well, the integral of x squared is just x cubed divided by 3. So this is just x cubed plus c. Tell you what, folks, one thing you can do, and it may be easy, but if you had a problem in calculus leaving off the constant term c, in differential equations, a lot of times the solution itself to the differential equation is contained with that coefficient for c. So throwing away c, you really just truncated about 98% of the answer. 98%. So c is important. So divide everything through by x cubed, so I get y is equal to 1 plus c over x to the third. Now that u, let's go back and see what it was. That u was y to the third, right there. So this is y to the third is equal to 1 plus c over x cubed. And we leave the answer just like that. Want to make sure I didn't want to go too far. And that's fine. Okay? So you should be good to go with the homework from 2.2 to 2.5. I'm not going to cover 2.6 as of right now, so we're going to stop here with this section. Okay? If you have questions about anything, let me know on Wednesday when we come back, and then I will also cover a review for the test. Thank you.